Section 2.1 and 2.2 of our textbook has to do with tangent lines. We are going to write the equation of a tangent line for a function at a point, find horizontal tangent lines from a derivative, and look at some graphs and derivatives. So we're going to be able to figure out today, based on a graph, if a function is differentiable or not. And part of that has to do with, is the graph continuous or not? So some of those things from Unit 1 are going to be showing up here again today. Since this is pieces from two different sections, notice that there are two different pages for the homework. Okay, let's start out by talking about finding the equation of a tangent line of a function at a point. So we want to find the EOT. So we've already done this a little bit, but we're going to use a little bit different notation for it. So for EOT, you need to find the equation for slope by taking the derivative. So that's going to be like your f prime of x is what we're looking for, equation for slope. Today, the different writing that we're going to be doing, we're going to start with our equations looking like y equals instead of f of x equals. But remember that f of x is just a fancy way to write y. So when we take derivatives today, instead of putting f prime of x, they're going to say y prime. Okay, like this, y prime instead of f prime of x. Okay, so after you find the equation for slope, you're going to substitute whatever the x value is into the derivative to find the slope of the tangent line, that is the SOT. You also have to find the point of tangency. Sometimes they give you the x value and the y value, such as examples 1 and 2 down here, and sometimes a problem might give you just the x value and you have to find the y value. So you also need the point of tangency. If they don't give you the point of tangency, substitute the x value into the original equation. EQ for equation to find y. All right, example 1, let's start off by finding the equation for slope by taking the derivative. If we start off with y, our derivative is y prime. So our derivative is going to equal, we're going to use the power rule on each one of these terms. So 4 is going to come down in front of the x, and then 4 reduced by 1 is 3, minus 3 times 2 is 6, x to the 2 reduced by 1 is 1, so we're not going to write a 1 there. And then plus the derivative of any constant is 0, because a constant has a slope of 0. So you don't have to put plus 0, it actually just kind of gets in the way. All right, so we're done with step number 1, find the equation for slope. Step 2, substitute x into the derivative to find the slope. That finds SOT, slope of tangent, SOT. So we're going to get y prime equals 4 times x cubed. So x is 1. If x is a negative number, we would use parentheses. It's not, so we get to be a little bit lazy there. Minus 6 times x is 1 again. So y prime is 4 minus 6, which means y prime is negative 2. So the slope of your tangent line is negative 2. That's like m. Okay, then your point of tangency was already given to you. It is 1, 0. Okay. Step 3, write an equation using the slope in point-slope form. So point-slope form starts out with the y minus y1 bit. I'm going to write it out with the whole thing, equals m times x minus x1. Make sure you've written that enough times that it is fully ingrained in your brain. The next thing I'll do is write out the skeleton form for it. That is just this part. Okay, and then we'll plug in some numbers. The x value and the y value go here and here. So the x value was a 1, it's here. Y value is 0, it goes here. And then m was our slope. Slope of tangent was negative 2. Boom, there it is. As a reminder for point slope form, there were minuses in the original form. So when you're plugging in positive numbers and 0, they're still going to have subtraction. So these will look opposite of how they look in the point of tangency. You can simplify this if you want. You would end up getting y equals, right, by subtracting 0, distribute out that negative 2x plus 2. And if there was a number sitting right here, we would add it or subtract it from both sides, which would affect the y-intercept over there. All right, so either one of these is a fine answer. Number 2. We are looking for the equation of the tangent line. So we need point of tangency and we need slope of tangent. We already have the point of tangency. Is given to us right there. Point of tangency means where your tangent line touches the actual graph. So this point is on this curve. If you graphed this, -1 would give you -2 for the y value. All right, so this is our original curve. It's some kind of a cubic function. Let's find the slope of the tangent and start by finding the equation for the slope. So y prime equals 3x squared plus the derivative of x is just going to be 1 every single time. It shows up constantly. Okay, so we have found the equation for slope. Whatever x value you plug in here will give you the slope at whatever point of tangency it is. So if we picked a different x value, we would find a different tangent line, which would mean the slope would be different. Let's plug in -1 everywhere we see an x. So y prime equals 3 times -1 squared plus 1. Because x was negative, I'm putting it in parentheses this time. Okay, super common mistake is not squaring the negative. So this is y prime equals 3 times. If you square a -1, you get a +1. So make sure you're doing that before you multiply times the 3. And last step, 3 times 1 is 3, plus 1 is 4. So y prime, which is slope of tangent, is 4. Okay. We need to write out y minus y1 equals m times x minus x1. And the skeleton form for that, boom. All right, the slope of our tangent line was 4. Slope is m, so 4 goes here. Point of tangency, I'm going to do this one in pink so it pops out of the page really well. So this point of tangency, this is x1 and this is y1. When we plug in a -1 here for x, it becomes a +1 because there was a minus. Minus a negative is positive. Same kind of deal happens over here with y1. y1 is -2. Y hangs out with y. -2 becomes a +2. If the problem were to say that you have to put it in slope-intercept form, you would distribute the 4 and then subtract 2 from both sides. Let's go ahead and do it because it won't take very long. 4 times x is 4x. 4 times +1 is a +4. And then subtract 2 from both sides. Y equals 4x plus 2. So this is a valid answer, and this is a valid answer. All right. The next bit is about finding a horizontal tangent line. So horizontal tangent lines happen when you have some kind of a curve like this. A horizontal tangent would happen at the very tip top of that. So this would be a horizontal tangent. Horizontal tangent lines also happen at the bottoms of curves. So at the very, very bottom, you could have a horizontal tangent. And that is even not a very good job. Straight across, horizontal tangent. So horizontal tangent lines, since they happen at the very, very top or very, very bottom, that's a special x value. We don't care about the y value so much generally. We care about the x value. So at what x value? How far over to the right do you have to go to get that horizontal tangent line? Where is that point? So since we're looking for an x value, that means we have to have some equation where we know some kind of a y value, and then we solve for x. Well, what do we know about horizontal tangent lines? We don't know the y value because we don't know the x value. But what we do know about horizontal tangents is that the slope equals 0 in both of these cases. So m or f prime of x or y prime, any of those guys would be valid. Okay. So we need to either have an equation that says m or y prime or f prime of x equals a bunch of stuff, and then we substitute out the y prime or the f prime of x or m. M is not very common in these cases, but substitute out the thing that means slope for the number 0. Okay. So that's what all this means over here. You take the derivative of the function to find f prime of x or y prime, and then you replace f prime of x or y prime with the number 0. And then you've got to solve. So 3 is going to be solve for x. Okay. Number 1, we've got y equals 1/3 x cubed minus 4x. I know we haven't seen any fractions in front yet. However, if we have a 3 as our exponent and then 1/3 is the coefficient, 3 times 1/3 is 1. So you'll see often that an exponent will match a denominator, and then with the multiplication that happens, they cancel and you're left with whatever the numerator is. That's a pretty common thing that calculus teachers and books make happen. All right, we got y equals, let's find y prime. Okay, 3 times 1/3 we said was 1. X to the 3 reduced by 1 is 2, minus 1 is the exponent here, so 1 times 4 is 4. Reduce that exponent, it becomes a 0. So anytime you just have an x, you know that the x is just going to disappear and you're left with this number. So that's going to happen a whole bunch. Okay, so we've done step 1, take the derivative of the function. Number 2, set the derivative equal to 0. So instead of y prime, you're going to put 0. So 0 equals x squared minus 4. And step 3 is solve for x. There are lots of ways that you can do these kinds of problems where it's like x squared minus 4 equals 0. One way is to see that there's a difference of squares. A different way is to get x squared by itself and then square root. I'm going to do it both ways, and let's see if there are some things that jog your memory. So I'm going to start. The first way we're going to do difference of squares. So 0 equals parentheses x plus 2, parentheses x minus 2. And then you set each factor equal to 0. So we would end up with x equals negative 2, x equals 2. So at both of those x values, you are going to have one of these kinds of things on your picture. So either the top of a curve or the bottom of a curve. So you would get a horizontal tangent line either way. I'm going to show you how we get a common mistake if we do it the other way. I'm going to add 4 to both sides, so we get 4 equals x squared. And then since it's an x squared, how do you get rid of a squared? You take the square root of both sides. What's the square root of 4? 2. So 2 equals x. But hang on a second. Didn't we just say that x could equal negative 2 also? What are we missing? Here's what's up. Anytime you physically write out a square root that was not there before, you have to put a plus and a minus sign in front of it. So when you choose to take a square root, you've got to put a plus and a minus. So that's a super duper common mistake. It's definitely safer to do difference of squares because this is really commonly forgotten. However, if 4 was a oh my gosh, not a perfect square. If it was like a 5 or something, then this would be plus or minus the square root of 5. It wouldn't come out pretty. But that's the example. Number 2, y equals the sine of x plus 5. So we're going to start by taking the derivative of both sides. The derivative of y is y prime equals the derivative of sine of x. So we did that in the previous video. The derivative of sine of x is positive cosine x, plus the derivative of a constant. Remember, constants are horizontal lines which have a slope of 0. So derivative of 5 is just 0, nothing. Okay, so we got y prime equals cosine x. Set cosine x equal to 0. And then we solve for x. Where does the cosine of x equal 0? I'm going to graph it just to get that little memory jog. Graphing cosine. Cosine starts at 1. So it starts up here, goes down here, and then back up, and then kind of goes that way and keeps on going. So at 0, at pi, at 2 pi, and so on, you would end up at the very tip top or very bottom of a curve, which is where tangent lines are horizontal. So the x would equal 0, pi, 2 pi, and so on. In a problem like this, you would generally be given some kind of a domain. So they would say like between 0 and 3 pi or something, not inclusive or inclusive. So you do have to pay attention to endpoints there. It's like, what are the x values that would be true? Last one, number 3. We've got y equals 6x minus 4. Let's take a derivative of both sides. Derivative of y is y prime equals derivative of 6x is just 6. Derivative of negative 4 is 0. So we've got y prime equals 6. Let's set y prime equal to 0. So 0 equals 6. There's no x to solve for. This does not work. This is like a no solution type problem that you've done in algebra. So nowhere on the graph of y equals 6x minus 4 does y prime equals 0. There is no horizontal tangent line. So no horizontal tangent. Okay, let's think about what the graph looks like. If we graphed y equals 6x minus 4, 1, 2, 3, 4. 6 has a slope there. That's a straight line. It's linear. That's an ugly straight line, but it's there. Okay, nowhere on there do we have a horizontal tangent line. Nowhere is there a slope of 0. If the equation was just like y equals negative 4, okay, so this is totally hypothetical. If it said y equals negative 4, y prime would equal 0 because the whole thing would be its own like horizontal tangent. Okay, the whole thing would have a slope of 0. Okay. Next page, differentiability and continuity. This is all from section AP 2.4. So if you're looking for examples of these types of problems, you can find them there. Differentiability and continuity. So we talked about an alternate definition of a derivative that uses limits. That definition is particularly useful when we're trying to figure out the relationship between differentiability and continuity. So continuity means that you can draw the picture and you don't have to pick up your pencil, right? There was that 3-part definition of continuity as well, which was that the left side, right, x approaches C from the left, and the right side limit, x approaches C from the right. If those two limits are the same, heck yeah, that's awesome. But this is not just f of x. Okay. So continuity was that the limits of f are equal, right? Limit from the left and limit from the right give you the same number. Also, we had to have f of c being defined, and that had to actually fill in the hole. So the reminder of what that looks like, I'll draw it out here. So the left side and the right side had to match up. So that means that the limit of f of x as x approaches c has to exist. It has to equal a number. I'm going to say it's L. That's going to be our y value. And f of c had to equal that same number, L. Like there had to actually be a point there. So then these things are going to equal each other. This is f of x. The difference between that and what we're talking about now is that we are finding the limit as x approaches c from the left and the right, that's the same, of the slope, right? This looks just like your slope formula. So we are finding the derivative of f at x equals c. Okay, so we're finding the limit of the derivative instead of the limit of the original function. That's the difference. Okay. So let's talk about differentiability based on a picture. Let's start with f of x equals the absolute value of x minus 2. So we're going to find the limit. We're going to find the limit of f prime of x instead of f of x because we're trying to figure out if our graph is differentiable. Okay, is f differentiable? Let's English this up here for a second. Sorry, I didn't do this already. Are we able to differentiate? Differentiate does not mean find the differences. Differentiate means find a derivative. Are we able to find a derivative? If we find the limits of f prime of x from both sides and they are the same number, then f is differentiable. Okay, so here we go. Here is f prime of x. Okay, just like we talked about up here, that's f prime of x, the limit as x approaches 2 from the left. So looking at our picture, we're approaching 2 from the left-hand side. What is the slope? Well, this is a straight line. I mean, if we ignore the right-hand side, this piece is a straight line. You can find slopes of straight lines by using rise over run. So if we start at a point and move down 1 and then to the right 1, we end up on our line again, or down 2 and right 2, and you can simplify. Okay, that is a negative slope. So from the left-hand side, we get negative 1 over 1, which is negative 1 as our slope. Use a different color for the right side, coming in from the right. Our slope, if we start here and end here, we move down 1 and left 1, or up 1 and right 1, it doesn't matter. We have a positive 1 for our slope. Are those numbers equal? No. Okay, since the one-sided limits are not equal, we can conclude that f of x is not differentiable. Not differentiable. And has no tangent line at x equals 2. Now, f of x is only not differentiable at x equals 2. If we were to take a random sample of this, a sample of it, and we ignore the 2, f of x is differentiable everywhere over here. F of x is differentiable everywhere over here because the slopes are all the same on this side, and they are all the same on this side. Okay. So we are only not differentiable at that one specific point. Okay. That one specific point has a sharp turn. So how can you tell if something is not differentiable when you're looking at a graph? If you have a corner or a cusp. So corners are like the V's. A cusp is like this. Okay, so it looks more like, I don't know, like a weird little bird picture. When you have square root functions, they tend to look like this, right? The little teapots. All right. But let's take a look at the continuity of f of x. I know we're spending a while on this problem. Continuity. Is f of x continuous? Yep, didn't have to pick up. Yes, f of x is continuous. So f of x is continuous, but it is not differentiable. So I'm going to write that in a different way. F of x can be continuous when it is not differentiable. When it is not differentiable. Okay, I'm writing that out very specifically because it tends to show up in like multiple choice. So just because the problem is differentiable, it doesn't mean it's continuous. Hang on. Just because the graph is continuous doesn't mean it's differentiable. That's the big deal. I think I said it wrong just a minute ago. F of x can be continuous, but not differentiable. If you're like, the graph is continuous, you still have to test if you can take the derivative everywhere. Okay. A graph with a vertical tangent line. So we haven't seen one of these yet, but if we take a look at this graph of f of x equals x to the 1/3, which is the same thing as f of x equals the cube root of x. Those are the same thing. I've not taken a derivative. They're the same function. That's this. It's like the teapot with then another teapot over this way. Okay, f of x is continuous at x equals 0. It's continuous everywhere. Okay, the limit, though, as x approaches 0, let's take a look from the left-hand side and from the right-hand side. If we come up from the left-hand side, our numbers are getting very, very big, right? Very, very, very big. If we come in from the right-hand side, they're also getting really, really big. We end up having a vertical tangent line. Now, I know when we talked about tangent lines before, I said that tangent lines just like skim across, okay, like a tangent over here would skim across and does not actually cross through your function. There are weird cases like this where the tangent line goes through your function. So we just like skim across this piece and we kind of skim across this piece. The tangent line is vertical. Okay, let's take the limit. F of x is x to the 1/3. So this is the limit as x approaches 0 of x to the 1/3 minus f of 0. F of 0 is the y value. So the y value when x is 0 is 0. On the bottom is an x, and then minus 0. That's the x value, and that's f of x. Okay, so this equals the limit as x approaches 0 of x to the 1/3 over x. Doing some little algebra, if we take 1/3 and subtract it from 1, we get 2/3. The bigger portion of x was in the denominator, so x to the 2/3 is in the denominator, and we need something on top. The coefficient was a 1, so put a little 1 placeholder. All right, if we plug in 1, that doesn't do anything. We plug in 0 because x is approaching 0. So this is going to equal 1 over 0. If you have 1 over 0 or any number over 0, that is undefined. So the slope is undefined. What kind of a line has undefined slope? A vertical line has undefined slope. So this is not an asymptote. not asymptote, Y-M-P-T-O-T-E, there we go. So it is not a vertical asymptote. The tangent line's slope is undefined. Okay, so tangent line, we're right there. I keep wanting to ask you guys if you have any questions, but it's really hard for you to do that because you are not here. All right, next little bit. Differentiability implies, oh, I'm sorry, we didn't finish talking about that one. So if there is a vertical tangent line, also the slope does not exist. So if you have a vertical tangent line, that means that your graph is not differentiable at that value. So the value was x approaches 0, so at x equals 0. You can find all sorts of tangent lines all along the other parts. It's just at that point where it's all messed up. Last little bit. Differentiability implies continuity. So remember how just a minute ago we said that f of x can be continuous but not differentiable. That's like right here. Our graph is continuous, but we cannot take the derivative at that spot. Okay? The opposite, though, has to be true. If your graph is differentiable, then the graph had to be continuous. Okay. I'm going to say that a different way. You have to have a continuous graph for it to be maybe differentiable. So this is the backwards of it. If a graph or a function is continuous, it might be differentiable. So if a graph is continuous, it might be differentiable. If a graph is not continuous, then it is not differentiable. So this does not mean that if a function is continuous, it's also differentiable because of the things that we've done on this page so far. Graphs with either a sharp corner or a cusp, which was this thing, so corners and cusps, or a vertical tangent line are not differentiable at a point where either of those actions occur.